Okay. So get this, scientists in Hong Kong, they're making some big waves with this new carbon capture technology.
Yeah.
And it seems like it has the potential to totally change the game.
It really does.
So we're diving deep into their research today.
Yeah.
To figure out what exactly is everyone so excited about?
Yeah, it's not just hype either. This research is going deep into some pretty extreme chemistry, actually.
Okay.
They're using supercritical water to try and unlock new pathways for capturing CO2.
Supercritical water.
Yeah.
That sounds like something straight out of a sci-fi novel.
It does sound like that, right?
Yeah.
But it's totally a real thing. And it's actually a key part of understanding this breakthrough.
Okay.
So just imagine water that's heated up and pressurized to the point where it's not really a liquid or a gas anymore.
Okay.
It becomes this strange, powerful solvent that can do some pretty incredible things.
Okay, wow. So they're using this super-powered water to react with CO2.
Exactly.
Then what happens?
So here's the really surprising part. They found that in this super extreme environment, a molecule called pyrocarbonate, which scientists used to think was way too unstable to be useful,
Right.
it actually plays a crucial role in how CO2 reacts.
Wait, hold on. So something that we thought was basically useless turns out to be super important.
Totally.
That's a pretty big deal.
It's huge. It suggests that we might have been looking in all the wrong places for carbon capture solutions this whole time.
Wow.
And to make things even more interesting, all these reactions are happening in something called nanoconfined environments.
Nanoconfined environment.
Yeah, so think tiny spaces on the nanoscale.
Okay.
Almost like little reaction chambers.
Oh, so it's not just the supercritical water.
Right.
It's also the environment itself that's making all this work.
Exactly. It's like they created the perfect recipe for carbon capture.
Oh.
The supercritical water plus these nanoconfined spaces are what's allowing these pyrocarbonate ions that were super fleeting before to become much more stable and actually play a significant role.
That's mind-blowing. So are we talking about some special material that creates these nanoconfined spaces?
That's where things get even cooler. The researchers have already found some materials that can create these environments.
Okay.
Including a naturally occurring mineral called magnesite.
Magnesite. So we're looking to nature.
Yeah.
For clues on how to design better carbon capture tech.
Nature is seriously an incredible engineer.
Yeah.
And magnesite forms under these high-pressure, high-temperature conditions, just like the supercritical water we've been talking about.
Okay.
So if we can figure out how it works in those environments, it could be a total game changer.
Okay, I'm starting to see how all this connects.
Yeah.
But how did they even figure out what was happening at such a small scale?
Right.
It's like trying to watch a molecular dance or something.
Yeah, that's where they bring in some serious computational power. They used a method called first principles Markov modeling to simulate these reactions and analyze the pathways without any human bias.
Oh, wow.
It basically lets the data tell the story of how these reactions unfold at the atomic level.
So they're using a supercomputer to watch these molecules doing their thing.
Pretty much.
Wow, it's like having a front row seat to a nanoscale show.
Exactly.
What else did they discover?
Well, they also uncovered a unique process called collective proton transfer, which basically means that protons, those positively charged particles and atoms, they're moving together in sync along these water chains during these carbonation reactions.
A synchronized proton dance. Okay, that definitely wins the award for the most visually stunning science concept we've talked about today.
Huh.
But how does this proton dance actually affect carbon capture?
Think of it this way. The way these protons move is totally different in these nanoconfined spaces compared to how they move in a more open environment. And this difference actually impacts the efficiency of the entire carbon capture reaction.
So we've got this unexpected molecule, these tiny spaces, and now a synchronized proton dance. This research is throwing a lot of curveballs our way.
And that's what makes it so exciting, right? It's challenging everything we thought we knew about carbon capture.
Yeah.
And it's opening up a whole new world of possibilities for how we can approach this problem.
I am definitely hooked.
Yeah.
This is way more than just some incremental progress.
Oh, yeah.
It feels like a whole new frontier of carbon capture is opening up right in front of us.
I agree.
But before we get too carried away with all the possibilities, let's bring it back down to earth a little bit and dive into the practical side of things.
Okay.
How can we actually use this research to create real-world solutions?
That's the million-dollar question, right? And that's exactly what we're going to be exploring in the next part of our deep dive.
I can't wait.
Yeah.
This is fascinating.
It really is.
Okay, so we just uncovered some seriously mind-bending science with this carbon capture research.
Yeah, it's pretty wild.
But let's be honest here. The real question is, can we actually use this stuff to make a difference in the fight against climate change?
Right. That's the ultimate goal, isn't it? To turn these cool lab discoveries into actual solutions that can work on a large scale.
Exactly. So let's talk about the hurdles here.
Right.
First off, these nano-confined environments.
Right.
Those tiny spaces where like all the magic happens.
Yeah.
How do we even go about creating those on a massive scale?
Right.
It's not like we can just shrink ourselves down to the size of a molecule and start building stuff, right?
I know it sounds kind of like science fiction, but that's basically what material scientists are trying to do.
Really?
We're talking about designing and manufacturing materials that have these incredibly precise pore sizes and surface properties to mimic those supercritical water conditions.
Wow.
It's a huge engineering challenge, but the potential payoff is enormous.
So we're not just talking about materials with tiny holes here.
No.
We're talking about custom designed spaces that can like optimize these specific chemical reactions.
Think of it like building a house for a very specific family.
Okay.
It needs to have all the right features and be built with the right materials to fit their needs.
Yeah.
And we're doing the same thing here, but on a molecular level.
Okay, so we need these highly specialized materials. Are we talking about like some rare earth elements or super exotic substances?
Well, actually, some solutions might be right under our feet.
What do you mean?
Remember magnesite, that natural mineral. It forms under high pressure and temperature, just like those supercritical water conditions we talked about.
Right.
So researchers are looking into that, but they're also exploring synthetic materials like metal organic frameworks and zeolites, which we can tailor with crazy precision.
So we're basically combining nature's blueprint with our own ingenuity to create these like carbon capturing powerhouses.
Exactly.
Okay, it sounds like we're on the verge of a material science revolution.
It's pretty exciting.
But even if we can create these amazing materials, how do we actually integrate them into like our current industrial processes?
Yeah.
There's not like we can just snap our fingers and transform a power plant overnight.
Right. That's where the engineering challenges get really real.
Okay.
One approach is to develop these special filters or membranes that incorporate these materials.
Okay.
Imagine fitting these filters into like smokestacks so they capture the CO2 before it even gets released into the atmosphere.
So it's like adding an extra layer of defense, a carbon-catching net for our industrial emissions?
Precisely. And we're not just limited to filtering out existing emissions.
What else can we do?
We could design entirely new industrial processes around these new materials.
Oh, wow.
Like imagine a cement factory that actually uses these carbon capturing materials as part of its production process.
Okay.
So it's basically baking carbon storage into the building materials themselves.
Wow, that's thinking outside the box.
It's
amazing. So instead of just releasing emissions, we're turning them into like a valuable resource.
Exactly.
Okay, I can see the potential here, but let's be real for a second. All of this sounds super expensive.
It does.
How do we make this tech like economically viable? Something that businesses will actually invest in?
You've hit on a crucial point. The truth is, right now, carbon capture technologies are generally more expensive than just reducing emissions the traditional way.
Right.
But we have to remember that pretty much every groundbreaking technology starts out that way.
Sure.
As research continues and production scales up, costs usually come down.
Okay, so it's like a chicken and egg situation. We need investment to make it cheaper, but companies might not invest until the price tag is lower.
Right. It's a bit of a dilemma.
So how do we break out of that cycle?
That's where governments and policymakers have a huge role to play.
Okay.
They can create a market that encourages innovation and drives those costs down.
How would they do that?
Well, they could do things like put a price on carbon emissions, offer tax breaks for companies that invest in carbon capture, or even fund those large-scale research and development projects.
So it's like giving companies a little nudge or maybe a big push in the right direction.
Exactly.
Okay, I get it. But even if we get past these money problems, what about storing all that captured carbon long term?
Right.
We don't want to just create a ticking time bomb where all that CO2 is just waiting to be released back into the atmosphere.
Absolutely. The storage part is just as important as the capturing part.
Okay, so what are our options?
One promising approach is geological storage.
Okay.
Where you inject the captured CO2 deep underground into porous rock formations or depleted oil and gas reservoirs. These formations are like giant sponges that can trap the CO2 for thousands of years.
So we're taking a page out of nature's book again.
Yeah.
Using the Earth's own storage capacity to safely tuck away that carbon.
Exactly.
Yeah.
And that's not the only approach.
What else is there?
We could use the captured CO2 as a material to create valuable products like fuels, chemicals, or even building materials.
Oh, wow. So instead of just capturing the carbon, we're finding ways to actually put it to work.
Right. It's called carbon capture and utilization.
I like that.
Turning CO2 from a waste product into something valuable.
It's like alchemy, but for climate solutions.
Pretty much.
Okay, so it seems like there are a lot of possibilities here. But with any new technology, there are always concerns about potential risks.
Of course.
So what are some of the things we need to be careful about with carbon capture and storage?
You're right. We need to be aware of the potential downsides. With geological storage, for instance, there's always a slight risk of leakage where some of that stored CO2 could escape back into the atmosphere.
That'd be bad.
Yeah. So it's super important to choose the right storage sites, implement good monitoring systems, and have backup plans in place just in case.
So it's all about minimizing risks and being prepared.
Exactly. We also need to think about the environmental impact of the carbon capture process itself.
Okay.
Capturing and transporting all that CO2 uses energy, which could offset some of the environmental benefits.
Right.
So developing energy-efficient capture technologies and using renewable energy to power them is crucial.
It's like a delicate balancing act.
Yeah.
Weighing the potential benefits against the risks and the costs.
That's a great way to put it.
But what about the public perception of all this? Are people generally on board with carbon capture? Or are there concerns about its safety and effectiveness?
Public perception is a big deal for any new technology to be accepted. And with carbon capture, there are a lot of different viewpoints.
Such as?
Well, some people see it as a really promising tool to fight climate change, while others are worried about the costs and the risks. Some even argue that focusing on carbon capture could distract us from the bigger goal of cutting emissions in the first place.
So it sounds like we need to have some open and honest conversations about the pros and cons of carbon capture.
I think so.
We need to talk about these concerns head on and make sure that these technologies are developed and used responsibly.
I agree. Transparency, public engagement, and good scientific research are all really important.
Yeah.
If we want to build trust and make sure that these technologies are used in a way that benefits everybody.
Okay, so this has been a really insightful discussion about, like, the nuts and bolts of carbon capture.
Yeah.
There are definitely challenges, but there are also these incredible opportunities.
For sure.
But I want to shift gears for a second and talk about something that's been on my mind throughout this whole conversation.
Okay.
The deep carbon cycle.
Ah, that's an interesting connection.
Yeah.
You're right, this research isn't just about new technology. It's also about understanding the relationship between the carbon on Earth's surface and the carbon deep within the Earth.
So for those of us who aren't geologists, can you give us a quick rundown of this deep carbon cycle?
Sure.
Like, what is it and why should we care about it?
You can think of the Earth kind of like a giant layer cake.
Okay, I'm listening. Tell me more about this carbon cake.
All right, so you've got the crust, which is like the thin, crispy top layer. That's where we live. And then there's the mantle, the gooey filling. And deep down in the center, you've got the core, like the dense, hot heart of the planet. Now, carbon isn't just hanging out up here in the atmosphere. It's constantly moving between these layers over millions and billions of years through all sorts of processes, geological, biological, you name it. That's basically the deep carbon cycle.
So carbon's on this, like, epic journey, traveling from the air we breathe down to the fiery depths of the Earth and back again.
Yeah, it's pretty wild.
That is wild.
Yeah.
So what does this have to do with the carbon capture research we've been talking about?
That's what's so fascinating about all this. Remember those extreme conditions we talked about, the supercritical water, the crazy pressures, those tiny nano-confined spaces?
Yeah.
Well, those conditions are not just in labs. They're happening right now deep inside the Earth.
Oh, wow.
And it's down there in those extreme environments where carbon is constantly being exchanged between rocks, fluids, even living organisms.
So by studying how CO2 reacts in these extreme environments, we're not just figuring out how to build better carbon capture tech.
Yeah.
We're also, like, getting a better understanding of how the planet actually works.
Exactly. This research is giving us a glimpse into this hidden world of the deep carbon cycle. It's helping us understand how carbon moves and changes deep beneath our feet. It's like we're looking back in time to see how the Earth has managed its own carbon budget for billions of years.
This is blowing my mind.
Yeah.
So the same processes that could help us capture carbon from the atmosphere are already happening naturally inside the Earth.
That's right. It's like we're getting inspiration from the planet's own carbon management system.
That's amazing.
Huh.
And by understanding these natural processes, we might be able to design even better, more sustainable carbon capture technologies.
Exactly. It's like we're teaming up with nature to tackle this huge challenge we're facing.
It's humbling, isn't it? We're talking about these massive processes that have been going on for ages, and now we're trying to learn from them and apply that knowledge to our technology.
It really is humbling, but it's also super inspiring. It reminds us that we're part of something much bigger than ourselves. And nature has all these secrets just waiting for us to discover. Who knows what other solutions might be hidden within the Earth, just waiting for us to find them.
This deep dive has taken us from tiny molecules to these huge planetary processes. And honestly, I'm feeling both incredibly small and incredibly hopeful at the same time.
I think that's a great way to feel. Recognizing the immense power of nature, but also believing in our ability to learn from it and work with it to create a better future.
Yeah, we may not have all the answers, but this research shows that we're moving in the right direction.
I agree.
Well, on that note, we've reached the end of our deep dive into carbon capture.
It's been quite a journey.
We've explored this cutting-edge science, grappled with the challenges, and seen the incredible potential that lies ahead. What's the one thing you hope our listeners take away from all this?
I hope they remember to never underestimate the power of curiosity and the interconnectedness of everything. This research shows how exploring something as simple as CO2 reacting in water can lead to discoveries that go from the tiny scale to the planetary scale.
It's a good reminder that science is full of surprises, unexpected connections, and the potential to really change the world.
Couldn't have said it better myself.
And to you, our listeners, keep exploring, keep asking questions, and never stop believing in the power of human ingenuity to make a better future. Thanks for joining us on this incredible journey.
Until next time, keep diving deep.